That's fine. I'm just saying, I'm saying, well, it's fine, but not getting
I'm probably going to take 127.
I'm gonna be in class with.
Yeah, most likely. Yeah. Yeah.
Yeah, they don't have.
We gotta take
So I'm not.
We're gonna have like a max loss discussion for 189.
Yeah, I haven't taken 189 actually.
I mean, I think you'll be caught up.
No, next semester is my last semester. So I was originally going to do it, and then I just figured with 106B it would be too much work. So yeah. Yeah, the whole core stuff is graduating next semester. Yeah.
Last semester.
We'll see. We'll see.
Three shift from 36 to unit point. Wait, what happens if there's like no?
We will find out. We will find out. No, so then the professors will just ask their grad students to do it, and then yeah, that'll be that instead. Yeah. Yeah.
Like if someone can get in here, you guys think
Yeah, that would be nice. That would be nice.
Yeah, like you driving. Adjoint. We just go for the final project. Which one do you mean choice for the final project? I'm not sure, but the fish but that one's like simply. Oh, let's do the delivery. You want to do the?
All right, cool. So I think we should be good to get started. Do you guys have just any general questions? Oh, yeah. Oh, should I move to the side? Oh, okay. Yeah, sure. Yeah, let me know if my head's in the way.
You know, what can you release sometime soon today?
Yeah, so homework will be released hopefully at the max an hour after law section ends. So yeah, that should be it. Yeah, so we only have 3 homeworks left for the class. Just as an administrative point, yes, we're nearing the end. So this next homework is going to be on Jacobians, which you guys probably started talking about. Then after that, we'll have dynamics, which I think will be a lot of fun. That's my favorite topic in this class. So I think you guys will really like that one. And then we'll do controls afterwards. So yeah, should be good. Oh, I don't think we're keeping track of them anymore at the moment. So if you just check on Gradescope, it should tell you a number of days. Oh no.
Yeah, for some reason it wasn't some release date and deadline.
Oh, okay. I can check for you later. Yeah. No. Yeah.
So I noticed the points include the extra credit. So we just subtract those 5 points extra credit and whatnot, then that's like the actual break.
Yeah. So the extra credit will be rolled in at the end. Yeah.
While we are on the topic, if we use like some of the slip days we had, but then like that homework eventually turned into a drop because of the score. Do we get the slip days back?
You don't, unfortunately. I'm sorry. Yeah. So we're just going to automatically drop your lowest score at the end of the semester. Yeah. Yes. Yeah. So you have to fill out. So if you filled out the previous feedback form and then the next one after midterm. Yeah. Yeah. So we might also have like a mini extra credit assignment after we do dynamics, but we'll see. We're still figuring it out. Yeah. Okay. Cool. So we can get started on talking about today's topic, which is all about rigid body velocities. So we're going to start out by just motivating rigid body velocities, why we care about them, why we actually need to spend so much time on them, why they matter. And then afterwards, we're going to talk about a good method for finding them very quickly. We're going to show where that method comes from, how we can apply it. And finally, we're going to finish off by talking about the adjoint, which is all about how we can transform these rigid body velocities and work with them in a very easy way. Okay, cool. So yeah, I guess just any other questions before we get started? Or all right, let's get into it. Okay, so what is a rigid body velocity? Why does it matter? Let's just start by thinking about like a simple case, right, where we have a particle that's moving in space. Okay, so let's examine motion of a particle. Right? What is rigid body, or excuse me, what does just velocity mean for a particle? Right? What is the actual quantity? Well, I'm just going to sketch out a little coordinate frame over here. Okay. And we're going to have this particle that is moving through space. All right. It's going to move according to this trajectory P of t. That's just going to be a 3D trajectory, right? It's going to have an X, a Y, and a Z coordinate. It's going to be changing in time, right? So maybe it'll be passing through a curve that looks like this in space, right? Going over there as time goes on. So what does the velocity of this point look like at every different point of this trajectory? Well, the velocity is going to be tangent to this curve at every single point in here, right? It's going to be this tangent vector that tells us where we're headed, all right? So how do we define this mathematically? Velocity is defined, we'll call it v of t equals t. Okay, so it's the derivative of our current position vector with respect to time. Okay, so if our position vector p of t is equal to x of t, y of t, and z of t, what's our velocity going to be? Well, our velocity will just be the derivative of each of those components in there. Okay, so it's going to be like dx dt, dy dt, and dz dt. Just extend the time like that. Okay, so whenever you take the derivative of a vector, you're just taking the derivative of everything that's inside. All right. So because it's this derivative, right, we know derivatives are always going to be the tangent lines to a curve. So that's why we end up with this property that these velocity vectors are always just pointing tangent to our trajectory in space. Okay. So what are the units of velocity? Well, velocity is, we have this dp up there, right? It's going to be some tiny change in position, and we have some dt. So this is going to give us units of maybe meters, right? Or some measure of distance over some measure of time. Right? So we're going to have meters per second. Okay? So all that is telling us is just how far we're going for every tiny amount of time that passes. All right. So that's what it means for the velocity of a particle. Right? But now we want to try and generalize this to rigid bodies. Right? Think about how these more complex bodies are going to be moving in space. Now, just something that I'd like to highlight is that oftentimes in this class we use this dot notation to denote derivatives. So if you see p dot of t, this dot just means that we're taking the derivative with respect to time. Okay. So dot equals time derivative. All right. So similarly, like if you see p double dot, that's just the second derivative with respect to time. Right. So second derivative with respect to time. Okay, cool. So how are we going to start to formulate these for rigid bodies? Right? What are some problems that are going to arise? Why might it be a little bit more complicated than the simple case of the particle? Okay, so what about rigid bodies?
I'm sorry, just say 1 second.
Oh yeah, sure. Yeah. All right, so let's just start out by sketching out a rigid body that is moving with some angular velocity and some linear velocity in space. We'll see how it works. Okay, so once again, we're going to have a coordinate frame over here. Right? And let's say that this is going to be a rigid body. You just draw this little blob in space. Okay? So let's say that this rigid body is going to be rotating about this axis, like that. It spins like that, some omega, right? And in addition to spinning about this axis with this velocity omega, it's also going to be translating in space. This whole thing is going to be shifting with some linear velocity v, right? So now we have two components. Okay, there's two things for us to worry about. So we have this angular velocity, which is given by this vector omega, right? It's this axis that we're spinning around combined with how fast we're actually spinning around it. So it tells us how quickly we spin. And then we also have this linear velocity that's pushing this whole body uniformly in space. Okay, so we also have a linear velocity. So what this means is that if we're trying to track the position of some particle, right? Let's say we have this point P over here. We're trying to figure out where this is going in space. It's not good enough just to simply like take the derivative, right? Or just look at where this position is going in space, right? It's going to be a lot more complicated than that, right? Because now we have all of these different components that are contributing to it, right? So we have this linear velocity, which is giving it some speed in that direction, and we have this angular velocity, it's giving it some speed in that direction, right? We have all these different vectors that are adding up to give us, this total velocity of this particle in space. Okay, so that's one thing that we have to be concerned about. Then another thing is, if we take a look at some particle, I'll call it P2 down here, this is actually going to have a different velocity than this other particle, right? So this is a big problem. P2 has a different velocity. Oops. Why is that, right? So, this whole thing is being shifted with this linear velocity v, but it's also being spun around this axis, right? So if I take my pen here and I just spin it around on this axis, this point all the way on the outside of my pen is tracing out this huge circle, right? But the closer I move in, the less distance that's actually moving, right? So to get all the way in here, it's not actually moving at all in space, right? It's just spinning. So what we know is that our actual distance to the axis is affecting our speed of our particle, right? So distance to axis, speed. So what this tells us is that pretty much every point on this rigid body is going to end up with a different velocity in general, right? If they're the same distance from the axis, sure, maybe they'll end up with the same velocity. But for all of these different points, right, we're going to have these different velocities pointing in different directions in space. Okay, this is going to be a big problem for us in general, right? When we were just looking at that single particle, we were just focused on that one point. That wasn't a problem. But if we're trying to somehow describe the motion of this entire rigid body, this is now a problem that we have to deal with. Right? Now, all these different particles will have these different positions, these different distances from their axis location, and give them different speeds. So we need to figure out some really nice way to describe that, right? So how do we describe the velocity of not just one, but any point on a rigid body? Any point on a rigid body. Okay, so that's going to be our focus of this idea of rigid body velocity. It's going to give us a really nice way of describing how fast any single point is moving on this rigid body. Okay, cool. So let's get started with trying to describe this behavior, right? So let's just arbitrarily pick this point P over here, right? So I'm just going to say, all right, that's some random point. It's got some Px, Py, Pz. This is going to be that point that we focus on, that we try to figure out its velocity. And I'm going to have two coordinate frames here that are going to help us set up this problem, right? So at this point, we're trying to go from this abstract idea of what a velocity is, to how quickly our positions move in space, to something a little bit more grounded and mathematical, all right? So to do that, I'm going to label two coordinate frames, all right? So one of them is going to be frame A over here. This is fixed in space, okay? So fixed in space. And because it's just fixed in space, we call it the spatial frame. Okay, so just like we have this frame that's fixed in space, if we're trying to describe where this body is going and how quickly it's moving, it's going to be convenient to have a frame that's fixed to the body, right? That moves with every motion of this rigid body. So I'm going to call that one the body frame. So maybe it'll look something like that, right? So this frame over here, frame B, is the body frame. Okay, so if this body translates or if it rotates, this frame is following every single motion of that, right? It's going to be tracking every single little motion. All right, now we're going to have two representations of our point P with respect to each of these frames. Right? It's just our same stuff that we were all doing before with these rigid body transformations and representing points in different coordinate frames, all the same stuff. All right, so the vector pointing from the spatial frame to our point P, right? I'm just going to call that QA. Right, so that's the position of point P as seen from the spatial frame. Okay, so position from the spatial frame. Now, what about from the body frame? Well, if we call that other one QA, I'm just going to call this QB. All right, so QB is going to be where this looks like in the body frame. Yeah. Yeah, so these are just position vectors. Yeah. Right. So do we have any questions just about this setup so far? What these frames are doing, how this body is moving, or why we even want to be talking about this? Yeah.
Like pertaining to your last introduction for a question, Professor was talking about how when you're designing like roller coasters with robots, for example,
yeah,
speed matters so that the head doesn't end up touching the ground.
Sure.
how is that relevant? How does like velocity help with like not having the head be cut off by like touching the ground or something?
Yeah. So I don't know. That's
Well, like how's velocity helpful?
okay. Sure. Yeah. So if we're trying to design, like, say, a controller for a rigid body, right? That's trying to like very, very precisely control the motion of this body in space. Like, let's pretend that this is like a little drone, right? We don't only want to be able to track a position, but we want to give it a certain velocity that it needs to track as well, right? Say maybe we're going to head over there. We don't just want to go to that position straight up, right? We're not just going to teleport over there. We're going to have some sort of smooth trajectory that we're going to follow on the way. So to do that, we need to give it a rigid body velocity that tells us, how fast it's going to be going each point in time as well.
And does that need to be constant or could that be variable?
It could be varying with time. Yeah, great question. All right. Yeah, do we have any other sort of motivation questions or set of questions? All right, cool. Okay, so if we're trying to describe the velocity of any point on a rigid body, maybe we'll just start by describing the position of these points, right? Try taking some derivatives. We'll see if we get any simplifications, any important results coming up. Okay, so here's what we are going to do. We are going to start out by writing everything in homogeneous coordinates, right? When we're working with these rigid body transforms, we write things in homogeneous coordinates. Okay, so let's write out the relation QA and QB in homogeneous coordinates. Okay. So we know, just using these ideas of rigid body transformation, right, that QA is equal to the transform GAB times this point QB, right? So GAB is just going to be our transform between the spatial and body frames, right? It's frame A over here and frame B. Same stuff that we've been doing so far, okay? So now what we're going to do is we're going to try and figure out how quickly this point is moving in space, right? So earlier we said we just take the derivative, right? P dot. So let's try taking the derivative of QA and we'll see what happens. All right, so let's take derivative. Derivative of QA. Okay, so I'm going to say QA dot is equal to GAB dot times QB plus GAB times QB dot. Okay, so remember, just that dot means that we're taking the time derivative here. Okay, the reason we ended up with these two terms is that just use the product rule from calculus. All right, so let's see if anything drops out when we do this. Well, right away, let's take a look at this QB, right? We know that this frame, this body frame, is always going to be following every single movement of this body, right? So will that point QB always remain the same? Well, if we're turning our rigid body, right, and we're just looking at what happens with that point, so we're moving this frame, that point's always going to look the same, right? Like if I take a look at this point on my pen, and I start spinning my pen around in space, from a frame that moves with it, right, that's never moving, right? This QB is going to be constant in time, right? QB constant. Okay. Now, what's the derivative of a constant? The rate that it's changing, constant's never changing. So this entire term is going to drop out. Right? QB dot is equal to 0. All right, so what does that give us? Gives us QA dot is equal to GAB dot times QB. Okay, so right here, we're just saying this GAB dot, the derivative of the transformation matrix with respect to time, multiplied by our points in our body frame, will give us our velocity of this arbitrary point on this rigid body in space. Okay, well, that's pretty good. That's not a bad transformation that we got right there. But something that might be even better is we want to find a map from a point in its spatial frame coordinates to its derivative in the spatial frame, right? This way, we won't be mixing up our different frames here. We'll go from spatial frame to spatial frame. Right? So how can we find map from a point in the spatial frame to its velocity in the spatial frame? Spatial frame. Okay, so what are we going to do? We're already pretty much there, right? If we look at our transform GAB, we know that the following is true, right? So we know that our point QA is equal to GAB times our point QB. Right? So if we want to just figure out what our velocity will look like in the spatial frame, all that we want to do is just get rid of this point over here. Right? If we get rid of that point, maybe we'll have a map from the point on that spatial frame to its velocity in the spatial frame. Okay. So let's just isolate QB on one side and go ahead, plug that right back into this expression. Right. So I'm just going to multiply by the inverse of GAB on both sides. And we're going to end up with QB inverse times QA equals QB. All right. Now we'll just substitute that back into the expression earlier. And what we end up with is, after substituting, we're going to get QA dot is equal to GAB dot times GAB inverse times QA. Now, what is this right here? All right. So what we've done is we've taken our point in the spatial frame, right? Point in spatial frame. We've multiplied it by some transform over here. What we've ended up with on this side is exactly what we were looking for, right? That's the velocity of the point in the spatial frame. All right, amazing. So in conclusion, what we've done here is we found this matrix, right? GAB dot times GAB inverse that's taking us from any point in the spatial frame to its velocity in the spatial frame. Yeah. Oh, from this one today. Oh, yeah. Yeah, so earlier we had just said that QA dot was equal to GAB dot times QB. So then I'm just substituting that into this formula. Yeah, good question. Okay, cool. Oh, do you need a photo?
Yeah.
Okay. All right. Yeah. Do we have any other questions about this stuff over here that we have? All right. Let me know when you're. I'll talk. Okay. Sure. All right. So this was really exactly what we wanted, right? So if we look back up at our diagram, what is this doing? Well, it's giving us a map from our point QA to its velocity in space, right? So if this is QA dot, we found this matrix that took us from this point over to this quantity, right? This velocity, this tangent vector up to whatever particle we have in space. And since we chose this P arbitrarily, this is something that's just true for any point on our rigid body, right? It's pretty good. Okay. So let's talk a little bit more about this matrix over here that we defined, right? So right now, I'm going to label this matrix something kind of special, right? This is something that gives exactly what we want. So let's just give it a special name. So I'm going to call it VAB spatial, and I'm going to say that that's equal to GAB dot GAB inverse. Okay, all I'm doing is just naming that transformation. It's doing this map from position to velocity. Okay, so if we rewrite this expression, this gives us this QA dot is equal to VAB spatial hat times our point QA over there. All right. So what this is a transformation from position to velocity. Okay. So what's this transformation? What's its shape? What does it actually look like, right? What are all of the different components in this transformation? So what do we know about VAB spatial? Let's try and just expand this expression over here, this GAB dot GAB inverse, and we'll see what sort of conclusions we can come to. Okay, so let's expand VAB spatial. So along the way, we're going to sort of figure out why we're actually calling this VAB spatial, why this hat comes into play, all this different stuff is coming from. Okay, so for now, we just sort of treat that name like a black box. Don't worry about it, and we're going to sort it out in a couple minutes. Okay, so where are we going to go from here? Well, we know that this is equal to GAB dot times GAB inverse. Okay. So in general, what are our G matrices going to look like? We have GAB is going to be some rotation, RAB 0, some position, PAB, and 1 over there. Okay. So remember, when we're taking the derivative of these quantities, all we need to do is just take the derivative of each term inside it. All right. So nothing fancier than that. All right. So let's go ahead. Yeah. Yeah. So just take derivatives, we say element wise, right? So we just apply that to every little element. Okay, so what's this going to end up looking like? Well, we're going to have this VAB spatial hat equal to derivative of RAB, I'll just call it RAB dot. PAB, call it PAB dot. 0 stays 0, and 1 is a constant, right? So derivative of 1 is just 0 as well. Now GAB inverse, I'm just going to write out the formula for the inverse of GAB. Just remember, this is something that we're able to do in general. It doesn't take a huge amount of work to derive. So I'll just write it here just for our convenience. So it's going to be R transpose, negative R transpose times that point P, A0 and A1. And that's an RAB, AB, AB. Okay, so let's multiply this thing out. Let's see what we get. Let's see if we recognize any of the sort of terms or the structure of this matrix that remains. Great. So let's multiply out and check the structure. All right, what's this going to look like? Now we're going to see the spatial hat is equal to, we'll start with the first column, right? So we're going to end up with an RAB dot, RAB transpose, and down here we're going to have a 0, right? And what about the second column now? Well, we're going to have a negative RAB, negative, yeah. So negative RAB dot, RAB transpose times this point PAB, and we're going to have plus 1 times PAB dot, plus PAB dot, and down here we're going to have another 0. All right. So we've just multiplied these matrices out, and we've ended up with something that's in this form. All right. So let's look at the shapes of these different things, and we'll see if we recognize this as anything that we've seen before in this class. Okay. Let's go ahead and do that. Well, right over here, what do we have? Well, we have two 3x3 matrices multiplied by each other, right? So this whole thing up here is going to be a 3x3 matrix. Okay. Now what about this thing over here? Well, we see we have the single point PAB dot hanging around, right? So this is going to be a 3x1 vector, right? So overall, what shape is this matrix? This matrix is going to be in R4x4, right? So some 4x4 matrix, right? With this special 3x3 matrix up there, we have 3x1 vector over here. And beneath it, we have all of these zeros. So does this look like anything we've seen before in this class? What does this look like? What does this look like? Well, we know that when we write out the hat map of a twist, okay, we're going to get something of the form omega hat V 0, 0, right? And this is just pretty much that same thing as before, right? This is going to be a 3x3. This is going to be a 3x1. And then beneath, we have all zeros. So this is exactly the same form as the hat map of these twists that we've been using so far throughout this entire class, right? So it looks exactly like the hat map of a twist. So this is where this little hat in this VAB hat comes from, right? It's just referring to the fact that it looks exactly like one of these hat map vectors we've been talking about, right? So just like with this hat map, right, this xi hat, where we had this associated special 6x1 vector that went along with that, we can do that same exact thing for this VABS, right? If it has the same structure, we can apply that same operation just to turn it back into a vector. Did you have a question? Okay, cool. So just remember that if we have this xi hat, the corresponding xi just looks like V and n omega, right? So let's just do the same thing for this VABS and see what we get, right? So we're going to take the V map, we said, and turn this into a vector, all right? So let's turn VABS hat into a vector. Okay, and we're just going to pull out those corresponding terms and just pop them right back in their place where they need to be. Okay, so what's that going to look like? Well, we're going to have VABS, this time without the hat, right? So first up, we put this velocity term that we had right there. What was that equal to in our case? Well, it was equal to negative RAB dot, RAB transpose PAB plus PAB dot. Okay, so let's write that down real quick. Negative RAB dot, RAB transpose PAB plus PAB dot. Okay, so that was our first term once we do this V map. All right, yeah, I got that time right. Now the second term, right, it's RAB dot, RAB transpose. But that's still a matrix, right? So when we have one of these matrices, we could just use the V map as well, just to note that we're taking that back into a vector, right? It's a little bit clearer when we have these omega hats. Now we're just going to trust that it works out with that and actually prove that that's equivalent to one of these omega hats, right? One of these skew symmetric matrices. But for now, it's fine for us just to leave it like that. Okay. So underneath, we're going to write RAB dot, right? We transpose V map, just to denote that we're putting it in vector form. Okay. So all up, what's the shape of this thing? Well, this guy up here is going to be a 3x1 vector, right? And so this thing down here, the V map just spits back out 3x1 vector values. It's another 3x1 vector. Okay. So overall, we've seen that this VAB hat spatial will mimic the form of one of these psi hats that we've been talking about, all right? So because it does that, we can translate it back into this 6x1 vector, right? Element R6, that will communicate all of this information about what this rigid body is doing, okay? So our big idea, all of the info about rigid body velocity is encoded in this 6x1 vector outside VAB spatial. Okay. And just for convenience, since these terms are kind of long up here, we're just going to give them two special names. All right. And these names are just going to be inspired by what they're doing and how they match up with these terms inside. All right. So we're going to call this little VAB spatial and little omega AB spatial. Yep.
Besides the 3x1 matrix, is that a half?
Which one? This right here?
Yeah.
Oh, so that's a V. So that's taking this 3x3 matrix and it's putting it back into its 3x1 vector. So it's like when we have these omega hats, you take the V map of that, it takes it back to the original vector. Yeah, good point. All right. Yeah. Yeah, exactly. So it's going to be like exactly the form of these omega hats up here. It just looks a little funny because it's in this. Yeah. So you could actually prove that that's one of those symmetric ones, but we're just going to. Oh, so what's the V map again? Yeah. So earlier we had mentioned that if we have some vector like omega equals omega 1, omega 2, omega 3, we could take its omega hat, right? We're going to end up with this thing with all zeros down the diagonal. And we're going to have like some negative term, some positive term, minus a plus, and a minus and a plus, right? So it's going to be one of these symmetric matrices. And it's going to do the same thing as the cross product, right? So if you do like omega hat times q, that's going to be the same thing as omega cross q. Okay. So RAB dot RAB transpose is just going to be one of those. In this case, we're taking this V map, which just means we're going back from this matrix representation into this vector form. Is that good? Okay, cool. Sweet. Great. Oh, yeah, of course. All right, cool. So let's just summarize what we're doing with this VABS and how it got here, right? So summary, we found VABS, right? This was a rigid body velocity. And it helps us figure out the relationship between a point in 3D space and its velocity as we're going along, right? So we found that the derivative of a point in the spatial frame, QA dot, was equal to VABS hat times the point in homogeneous coordinates QA, right? And then once again, just remember that we define this VABS as VABS hat equals VAB dot GAB, okay? So these are just the key points for what this rigid body velocity is and where it's originates. Right? Okay. So do we have any questions about this before we talk about the body velocity? Sure, yeah. Okay, cool. So let's talk about the body velocity. All right, so I'm just going to go ahead and copy this image from up here. All right, perfect. Yeah, sure. Is that good? Or a little more? Okay. Yeah.
Did we start, so the spatial velocity started at like, at that picture, right?
Which one?
So like the whole started.
Oh, yeah.
So it's all right.
Yeah. So this like map over here was our VAB hat. Yeah. Sure. Yeah. Okay, cool. So let's talk about the body velocity, right? So up there, we found something that was contributing to our spatial velocity, right? We gave it a point in the spatial frame. What did it spit back out? It gave us a velocity in the spatial frame, okay? That was pretty handy, right? That's the most physical quantity we can measure. If I'm swinging my pen around, its actual velocity is really going to be with respect to something that's standing still, right? That's usually what we care about. But, you know, sometimes the need will come up for something else, right? We're always going around, we're always representing things in different coordinate frames within this class. We love doing it, we can't get enough. So let's try and talk about some ways that we could transform these velocities into a different coordinate frame, okay? And we'll see some of the mathematics that results from it. So let's remember what we were saying earlier. Earlier, we had said that QA dot was going to be equal to this GAB dot, GAB inverse times this point QA, right? So now, instead of doing this representation, what I want to try and do is I want to try and figure out what this velocity will look like from frame B, okay? So it's not that we're actually looking at the velocity of points inside frame B, right? If I'm swinging this around and I'm moving with that, everything's going to look like it's completely still, okay? All that we're doing is we're transforming the spatial velocity to be with respect to the basis vectors of frame B, okay? Yeah, so physically, what it would mean, I don't know. So there's not a huge amount of meaning to it. It's just something that turns out to be very mathematically convenient with us, especially when we're dealing with more complex systems. So all that we're really doing is I'm saying like, all right, I'm moving this over here. Now what I'm going to do is I'm going to take how fast that looks from my perspective, and then just shift it to be in terms of these basis vectors over here. So it's really just referring to the same physical quantity in space. We're now just representing it with respect to a new basis.
And is there a way, for example, we could measure that with respect to the body or not really?
Yeah. So we could measure it just using these transformation matrices, which we'll see in just a sec. But yeah, other than that, yeah, it's going to be pretty much the same. Yeah, sure. Okay. So what we're trying to do here is we're trying to take a vector from frame A, right, the spatial frame, and put it into frame B, the body frame, all right? That's something that we've been doing this entire class, right? It's going to be nothing more complicated than that, all right? So we'll try and take QA dot from the spatial frame to Q dot A in B, right? It's representation in the body frame. In the body frame. All right, so how are we going to do that? Well, we're just going to be applying the same transformation matrices that we've been doing this whole time, right? It's going to just be a simple coordinate transform, right? So we know that this transformation matrix, GAB, is something that takes us from frame B back into frame A, right? Now we're just trying to go the other way, right? We're trying to go from frame A into frame B. So we're just going to do GAB inverse times QA dot, okay? So Q dot A, represented in frame B, is just going to be the same thing, just applying this transformation matrix to that vector. All right, cool. So let's multiply this out. Let's use this full formula for QA dot, and we'll see if we can get some mapping from a point in the body frame to its spatial velocity as seen from the body frame, okay? So we're really just approaching this with the same velocity as before, right? We want mappings from things in their frame to things in their frame, right? We're just trying to keep everything very organized. Okay, so what we're going to do is try and find a map from QB to spatial velocity as seen from the body frame, all right? So spatial vel as seen from body frame. All right, so how are we going to do that? Well, maybe we could just start out by substituting in this formula for QA dot, right? We know that this gave us a mapping from QA to its velocity. Now, maybe we could do the same for QB. Okay, so we're going to start out with QA dot representing the body frame is equal to GAB inverse. Now I'm just going to substitute in this formula for QA dot. Okay, so it's going to be GAB inverse times GAB dot. GAB inverse times QA. Okay. This was just exactly that thing that we found out there. We haven't made any changes. We just substituted it right in. Okay. So what do we do? What are we going to do from here? Well, what we want to do is we're going to try and replace that QA with a QB, right? We're looking for a mapping from something in frame B to something in frame B. All right. We'll define a mapping from frame A to frame B. We're just going to refer to that GAB once again. Right? So we know that QA is going to be equal to GAB times QB. So let's substitute that in. GAB inverse, GAB dot, GAB inverse, all times GAB times our point in frame B, right? That's going to be equal to QA. All right, so QA dot B will be equal to all of this. But now we have two inverses next to each other, right? We have this and its inverse. So those two are going to be canceled. And what we're going to find is that the velocity of this point, as seen from frame B, is going to be GAB inverse, GAB dot, all times its representation, frame B. Okay. So this gives us exactly this transformation that we were looking for once again, right? So what we've done is we've gone from our point in frame B, we've multiplied it by the special transform, and what we've gone back out is the spatial velocity as seen from frame B. Okay, so this was our overall goal here, and the matrix that helped us achieve that was GAB inverse times GAB dot. Okay, so just like earlier when we had GAB dot, GAB inverse, there was this mapping from the point in its spatial frame to its velocity in the spatial frame. We call that VAB spatial. We're now going to be able to call this VAB body, right? Working in the body frame, we'll just call it VAB body. All right. So what we're going to say is we're going to define this new matrix VAB body, and that's just going to be equal to GAB inverse GAB dot. Okay. So that allows us to write derivative of QA as seen from the body frame is just equal to VAB body times QB. All right. Okay, so do we have any questions about what we did there with this body frame and shifting things around? How do we feel about that? Okay. Yeah.
Just still make sure I understand that. So VAB is velocity of point Q. Wait, like how do we refer to the V again? Like
Yeah, so this is just like VABB hat. This one over here. Yeah, so VABB hat is not a velocity, right? So this is it is a transformation that helps us find the velocity. Yeah, so that's a really important distinction to make right there. So when you see one of these big P's, it's not going to be containing the actual velocity. It's just something that helps us find it for any point that's out there.
what about the version without the hat?
So the version without the hat, we'll talk about that in just a second. Okay. Yeah, how we can like interpret those terms. Yeah, but they're going to be slightly different. All right. Yeah, that's a capital V, right? Yeah, that's a capital. Okay. So I'll draw the lowercase ones. Yeah. Okay. So, earlier we said that this VAB spatial can be broken down into this vector form, right? It's going to have this very special form that looks just like a twist. We could pull it back into vector form, okay? Now we can show that we can actually do that same exact thing with this VAB, right? So we can prove that VABB hat will be equal to some omega ABB hat, some little v ABB, and a 0 and 0, okay? So I won't prove this here, but it's going to be pretty much that same process that we did before, right? Multiplying these matrices out and seeing that everything will reduce to something that looks like this. Okay. Yes, yeah. Yeah, so this is your actual point in space. And then, yeah, this is the velocity over here. Yeah. Yeah, awesome. Okay. So now, if we want to get rid of this matrix form, we're going to take the VMAP, right, and put it into a vector. So this tells us that VABB is equal to, I'm just going to start out by extracting that velocity, putting it up top. v, and then I'm going to take that angular velocity component, right, matrix over here, and just put it into vector form, v omega ab, just like that. Okay. And what this gives us is something called the rigid body velocity. Body velocity. Okay. So if you're ever asked for the body velocity, you're going to be looking for one of these VABs. If you're ever asked for the spatial velocity, you'll be looking for one of those VABs. Okay. And the only difference is that this is something that's just working in the body frame exclusively. The other one's just exclusively working in the spatial frame. Okay. So in general, these are only two different types of velocities that we're interested in. All right. So summary. Let's just go ahead and just write out all of these important formulas that we need. Right? So we had this first velocity, VAB spatial hat, that was equal to GAB dot, GAB inverse. And we had like these little components in vector form. Lowercase VAB spatial and omega AB spatial, right? And what did this do for us? Well, it took us from a point in the spatial frame into the velocity in the spatial frame, right? QA dot VAB spatial hat, because we're interested in the transform in this case, times QA, right? So this was all for the spatial velocity. Spatial velocity. Oops. Okay. And then for the body velocity, what did we say? Well, we had VAB body hat was just equal to GB inverse, GAB dot, right? And we could extract back out this vector form from that transformation matrix, which gave us VABS. VABB equals lowercase VABB omega ABB. And we found that the spatial velocity, as seen from the body frame, was VAB body hat times your point in the body frame. Okay. And this was all for body velocity. Okay. So in summary, that's pretty much everything that we're going to need to know about these different types of rigid body velocities, right? That's where they come from. And the reason that we need them is that every point on a rigid body is in general going to be moving with a different velocity, right? So we want to find these transformations that will help us map from a point to its velocity in space. Okay. So these are helping us do exactly that. So map from the point to its velocity. Okay. Now just note that there is this other notation that's used in the textbook for this QA dot B and QA dot, right? So they call that like VQA is equal to that, and VQB is equal to that, right? And the reason that I tend to avoid this notation is that, I don't know, I think it's a little bit misleading, especially with VQB, because, I don't know, it gives you the idea that this is equal to QB dot, because this is equal to QA dot. But just remember, QB dot is equal to 0, right? Within the actual frame that's moving, points are never changing. Right? It's a rigid body. So just remember, when you see this VQB, this is actually just equal to VQA, QA dot, just seen from the body frame. Okay. So VQB is not equal to QB dot. Okay. So if you ever see that floating around, just remember it's not QB dot, it's just QA dot as seen from the body frame. Okay. So I know I've been saying a lot of the same thing here. I just really want to try that. But yeah. Okay, sure, yeah. Yeah, so if I have my pen over here, right, and I'm looking at a frame, it's moving with my pen as I'm moving around in space. With respect to that frame, right, everything is staying absolutely still, right? As I'm moving with it, it looks like none of these points on this pen are moving, right? Because it's a rigid body, all these points will always stay in the same position. Yeah, so when we say QB dot, we're taking the derivative of points within the body frame, right? So QB dot will be 0 because within the body frame, all these points are frozen, right? We're just moving with a rigid body. So what we're saying when we say VQB is we're saying, all right, we're spinning this around. What does that look like from space? It's going to be QA dot. We're going to transform that velocity just with respect to the basis vectors of the body frame instead. So it's going to be different than taking the derivative of actual points within the body frame. We're looking at how quickly it's spinning in space, and you just transform that vector into the body frame. Does that make sense? Okay. What part seems unclear? Yeah, you know, maybe it'll help if I just give like a numeric sample real quick. Is that good? Okay, cool. So let's say that we have, let me draw this a little smaller. Okay, so we have our frame A over here, right? This is our spatial frame. Okay, so let's say we're trying to figure out what the velocity of this point P is with respect to this like body frame. Oops. Over here, which is moving. Okay, so this is frame B. It's your body frame. All right, and this is attached rigidly to this body that's moving around. Okay, so our point QB will be what it looks like for the body frame, while QA will be this point over here. Okay, so what it looks like in the spatial frame. So we know that if this body is moving, it's like spinning around and it's also like moving in space. We know that QA dot is not going to be 0, right? Because it's actually moving with some velocity in space, right? So this is our spatial velocity. Okay, so I'm just trying to move this pen around in space. We know it's going to have some non-zero velocity, right? But now if we look at QB dot, right, and we start moving this around, right, this point P with respect to this frame B, spinning with this body, will always look the same, right? So QB dot is always going to be equal to 0, right? Because that's actually that vector, which will always be the same with respect to this basis. It's just spinning with that rigid body. It's moving and spinning with that rigid body. Okay. So what we're trying to do instead is when we say VQB, that's equal to QA dot represented in the body frame. All right. So let's say that like our QA dot might be something like 1 meter per second in X direction, 2 in Y, and 3 in the Z. Okay. And let's say as well that our rotation, RAB, is, I don't know, I'll just come up with something random, like 1, 0, 0, 0, negative 1, 0, 0, 0, negative 1. Okay. So all that we're doing is we're just trying to transform this into the other frame. Okay. So what VQB would be in this case is just this rotation. Like, let's just say that it's just spinning for now, times QA dot. All right. Yeah. Oh, so this is why I don't really like this notation. So it's not actually the velocity of point B. It's just the velocity of this point over here. That's just seen from frame B. So we're taking the spatial velocity is 1, 2, 3 meters per second. And all that we're doing is just applying this transformation to it.
Okay.
Yeah.
I guess, did you have a different notation than that one that you just were talking about?
Like this one?
No, the VQB that you said was confusing on the textbook.
Oh, yeah, yeah. So usually I'll just use QA dot with brackets and then write this B over here. So when you write like a vector with brackets and then B, that's just means that it's a vector represented in the B frame. Okay. Right. It's not equal to QB dot. Yeah. Okay. So what was I trying to do? Oh, yeah. So let me just write this as RBA. Actually, that's going to get shorter. Okay, so I'm just going to go ahead and apply this matrix RBA to get this vector into the B frame. Okay, that'll tell us that VQB, which is just QA dot, as seen from the B frame, is just going to be these components flipped inside. All right, so it's going to be like 1, negative, sorry, 1, negative 2, and negative 3. Okay, so all that we're doing is we're just changing the basis vectors that we're looking at that velocity from. We're not actually, doing anything in the B frame. We're just changing the basis. Does that make more sense?
Yeah.
Okay, cool. Yeah, do we have any other questions? It's kind of subtle concepts. So yeah. Oh yeah. Sorry, it's Vel. Yeah. Yeah. So that's what these like B hats are doing. Yeah. So whenever you see that hat, just remember it's an actual matrix. So it's transforming these points into velocities. Yeah. Yeah, so G will usually be time variant. Yeah.
The different rotation. Like how's?
Oh, yeah, so it's just like we're spinning around like this, so I could be having like this totally random pattern in space, right? So if we look at here to here, it's gonna be a constant rotation matrix, but if we shrink that down, that like frame down to a tiny, tiny interval, we're gonna end up with something that changes continuously with time, right? So if we just look at a simple like matrix like RZ of theta, right? Which will be equal to, I think it's cosine theta, negative sine theta, cosine theta, or did I get the sign mixed up? I think that might be over there. Yeah, it's one of those. 0, 0, 0, 0, 1, right? And we try and look at what that is equal to. Well, these thetas could just be thetas of time, right? So it's like as we're changing time, our rotation matrix is changing. So like time is going on and we're now at a different position over here. So if we take the derivative, like RZ dot, well, we're gonna have to take the derivative of everything inside there. So we end up with theta dot, negative theta dot, sine theta. We're going to have a negative theta dot cosine theta, and so on and so forth for these other terms in the matrix. Yeah, does that make sense? Or okay. Yeah, yeah. Now that's just actually changing time. Yeah. Yeah. Yeah, sure. Yes. So without the hat, that's just called like a rigid body velocity vector, right? Yeah. So sort of. So it's something that's a little bit more conceptual. So we'll talk about that in just a second. So this is actually our angular velocity. So that's our actual angular velocity. And this is going to be a component of linear velocity. Yeah, that's a lower bit. So the reason that we can't put the actual linear velocity in there is because that depends on the position of the body.
The VQA is basically the velocity of the sun.
Yes. Yeah. Yeah. So whenever you see that VQA or that QA dot, that's your actual velocity. Yeah, great questions. Yeah, like there's a lot of notation in this section, so it definitely takes a little bit of time to digest. Oh yeah, yeah. So it's sort of because of like what this VAB spatial actually is. So that VAB spatial is not like the actual spatial velocity of my point, right? Not so it's not quite that as well. So it's going to be the velocity of a very, very particular point within your frame. So it's going to be we'll talk about it in a little while. Actually, I don't want to spoil it.
Yeah, that's a big capital V, right?
Yes, that's a big capital V. Yeah. So that's actually going to be the very next thing we talk about.
I didn't see what. So this is. What you have here, like you're defining, it's the same as what we have inside, right?
What do you mean by that?
When you would actual angular velocity component of linear velocity.
Yes.
That's the same as what is on the right.
Yes. Yeah. So the reason that this is something that's non-physical is that this vector arises from the need to have a transformation, right? The reason that it works out this way is only that, because that's what the transformation required of us, right? We're ending up with these different components in here. That's why they don't just end up being like perfectly what we need. Yeah, so it's going to be part of our overall function. Yeah. Okay, cool. So how you guys feel? A lot better. Okay. So hopefully we'll make this all a little bit more concrete with just doing an example. So I'll talk about how we find these and then also how we interpret these different components in these rigid body velocities. Okay. So let's talk about finding and interpreting. Rigid body velocities. Okay. So let's talk about these formulas that we have over here, right? So we have this VAB hat S is equal to JV dot, JV inverse, right? And this other one, which was VAB body equals JV inverse, JV dot, right? So our big question here is, are these formulas practical to work with, right? Are they nice? So are they practical? Right? So even when we just tried to take the time derivative of RZ out here, right? We saw that we have to literally take the derivative of 9 components, right? That sucks. No one wants to do that, okay? So they're not practical at all. So what we would have to do here, right, is we would have to take the derivative now of 16 components in this GAB matrix, right? And take the inverse of this matrix and multiply all of this. So that's a huge amount of computation for us to do, okay? So what we're going to try and look for is some shortcut. That helps us find these vectors. Okay, and along the way, we'll sort of figure out what these terms within these vectors mean. Okay, so let's go ahead and try and set that problem up. Okay, so our big question here, is how can we find VAB spatial? We'll just start with the spatial one just because it's more easy to interpret. This component, little VAB spatial and omega AB spatial, right? Well, to find this, we'll need to find each of those components within there, right? We'll need to find this omega AB spatial and this VAB spatial. We must find the component. Okay, so we're sort of going to work this out with the help of an example. And just because I think it's kind of handy and you guys have all seen this one before, I'll just do the example from the homework. I think it was like question 1 on there. So if you haven't submitted it yet, don't worry about it, it's fine. But yeah, we're just going to go through that right now and then just make sure. Oh.
Question 4.
Oh, things could go up. Okay. Oh yeah, question 4 was a lot of calculations. So I won't do that one because that takes quite a while to do. But yeah. Okay, nice. All right, so let's just sketch out that scenario that we gave you in question number 1. Okay, so what we told you is that we had the spatial frame down here, right? So spatial frame, frame A, and we had another frame right over here, right? So it was pointing in a naturally different direction, right? So where this was our X, our Y, and our Z, all of a sudden, this was now our Y direction, that was our Z direction, and that was our X direction, right? So what we also told you was that it was only spinning around a single axis, Xi over here, just like that, right? Spinning in that direction, okay? So what we meant by that was that this little arm was going to be spinning around this single axis right over here, right? So this is sort of going to be tracing out this circular path in space as it goes along, right? So that one comes right to the origin and keeps spinning around this axis over here, okay? So just in terms of dimensioning this thing, what dimensions did we give? We said this was some length L2, this was some length L3, and this one over here was going to be, I think this one was L1, right? Okay, cool. So what we asked you was to find VAB spatial and VAB body, right? These vectors that help us find the velocities of these points on this rigid body. Okay, so where do we begin? Let's just start out by writing out our definition. VAB spatial, this again is just equal to VAB spatial omega AB spatial. Okay, so this problem is just going to boil down to finding convenient ways to figure out these little components in here. Okay, so we're going to talk about a method called the circle method. Circle method. It's going to make our lives really, really easy in these problems. Okay, so how are we going to break this down? How are we going to find each of these components without actually computing all those matrix derivatives by hand, right? All right, so how can we simplify our solution? All right, well, let's see how we might do that. So let's first of all just talk about angular velocity in general. Okay, so what's that angular velocity going to look like? And where does it come from? All right, so we know that in general, this is just going all the way back to the beginning of the class when we were originally doing exponential coordinates. We know that if this rigid body has this angular velocity vector omega, right? This means that it spins on the axis omega in space, right? And it spins with the magnitude of omega, right? So this was an angular speed, right? So it's our rate of change of our angle as we're actually moving around this point, right? So like if we take this over here, it's going to be tracing out this little circle in space, right? And if we look at that, that's our angle. So if we actually check the time derivative of our angle, right? Omega equals theta dot. That theta dot will just be equal to the magnitude of our angular velocity vector, okay? So this gives us our actual rate of rotation. Okay, and we said that if we wanted to find the speed of some point that was, being affected by this omega, we could figure out the speed by doing omega crossed with q, right? Where q was that little point that was, that vector that was giving us the distance to our axis of rotation. Okay, so distance to axis. Okay, so this was our general setup for this angular velocity over here. Okay, so why don't we go ahead and try and expand out the formula for spatial velocity that we found earlier, and we'll see if we can get a setup that gives us something that looks like this. Okay, if we can do that, then maybe we'll found what our omega ABS represents, right? Is it just this thing? We'll see. So what do we have? We have this VABS equals VABS omega ABS. So how do we apply that? Well, we know QA dot was equal to VAB spatial hat times QA. Right? And that was equal to omega AB spatial hat. Then there's this lowercase VAB spatial 0, 0 times this point in homogeneous coordinates, right? It was like QX, QY, QZ, and then a 1, something like that, right? Was equal to QA dot. Okay, so let's multiply this out. Yeah, Anya. Oh, yeah. So it's just like if I'm spinning this around, like this axis in space, like how quickly is the angle changing in there? Like in radians per second. So yeah, so it is the same as omega in the scalar case. So if you look at an equation like V equals R omega, and then in that single scalar case, then it's going to give us what we want. But now what we have is we have this vector in 3D that's giving us our angular velocity. So it's a little bit more complicated. So we actually have to take the magnitude of the vector now. Yeah, that's a good question. Sure. All right. So let's go ahead and let's multiply this out. We'll see what we get. Okay. And just for convenience here, I'm just going to be like a little bit loose with this homogeneous coordinate stuff. So I'll just point out which vectors are in homogeneous coordinates and which ones aren't. Okay. I'm just going to write that as a QA bar over there. And yeah, I'll just show you guys how this works out. Okay. So we're going to end up with QA dot. So this is now no longer in homogeneous coordinates. Right? That's just our actual 3D vector now. Is going to be equal to, let's just perform this multiplication. It's going to be omega AB spatial times our actual point QA, no longer in homogeneous coordinates, plus 1 times VAS. VABS. And underneath, we're going to have a 0. Right? So that whole thing underneath simplifies to a 0. We can just drop it and focus on that expression up top. Right? So QA dot, our actual 3D velocity of our point, is equal to omega ABS hat times QA. So that's going to be omega ABS crossed with QA plus VABS. Okay. And now what we see, oh yeah.
I'm just a little confused as to why you're saying this is not
Oh yeah, so it's just like we're taking ddt of QA and 1. So then that's just going to become QA dot and 0 in homogeneous coordinates. Yeah, great point. No, so actually there's this special quality of homogeneous coordinates where if it's a point in space, you're going to put a 1 underneath, but if it's a vector, which is the difference of 2 points, you can put a 0 underneath. Yeah.
Oh, okay, so then the entire vector itself is in homogeneous coordinate, but the QA itself is
Right.
okay.
Okay, awesome. So now what do we have right here? Well, we have this QA dot is equal to this omega AB spatial cross QA plus VAB spatial. And if you look back to how we define this angular velocity, right, you see that that's exactly that term that's right there, right? So what is omega AB spatial? AB spatial, right? This mysterious term, it was a result of our transformation. It ends up just being perfectly the spatial angular velocity vector, right? It's just the spatial angular velocity vector. Okay, so it's nothing more than that. That omega AB spatial just turns out to be that perfect physical quantity. Okay, so how are we going to actually go ahead and find that in this case? Actually, do we have any questions about that, like this interpretation of this thing before we continue?
What is the theory again? I'm sorry, where did it come from the side of the?
Oh yeah, so it's like
Okay, that's what I thought it was.
Yeah. Yeah, yes.
No, if you want, actually, that.
Oh, okay.
Yeah. I didn't know.
Yeah.
Yeah, that's okay. That's okay. I thought I double check.
Sure. Yeah, I'll just write that that's QA.
Thank you.
Sure. Alrighty. Cool. All right, so we have this interpretation for omega AB spatial across QA. Now, what will that be in this particular case, right? We now have an interpretation for this. Let's check back in our diagram and see if we can apply this interpretation to find out what it is. Okay, let's take a look at this. So what we know is that we're rotating about this axis, xi, in space, right? So what is omega composed of? Well, omega has two things, right? It has an axis of rotation and it also has a magnitude. Right? So if we know the direction that we're rotating around in space, that's just going to be our axis of rotation, right? So let's check what direction are we rotating around in the spatial frame. Well, we see that we're just rotating about this axis that points over here, right? In the spatial frame, that's just perfectly aligned with our y-axis, right? So we know that omega is just going to be in the direction of the y-axis, okay? So what this tells us is that omega AB spatial in this problem is in the direction 0, 1, 0, okay? So it's simply just pointing along the y-axis. So we're like, okay, the direction is going to be 0, 1, 0. Now what we need to find is our actual rate of angular change, right? Our speed. But if you guys actually check out the homework question, we said that you would be given theta dot, right? So you're actually given what this thing is already, right? So theta dot is our actual rate at which this angle is changing, right? The rate at which we're spinning around our axis. So we know that that's just the same thing as the magnitude of our angular velocity vector, right? So we're given how quickly we're actually spinning around that axis already. Okay. And direction 0, 1, 0, its magnitude, theta dot. Okay. So all that tells us is that our omega AB spatial is just going to be a 0, a theta dot, and a 0 for that case. Okay. So that gives us our first component of this vector, VAB spatial equals lowercase VAB, omega AB spatial. Okay. Yeah. Yeah, so if we gave you theta as a function of t, then you would have to take the derivative yourself, but I think we're pretty much never going to do that. Yeah. All right, do we have any other questions?
Sorry, I kind of blanked out on the question.
Sure.
Is it about if we are not given theta dot?
Yeah.
How we have to do it?
Yeah, so if you weren't given the theta dot, you would just we would have to give you the angle as a function of time, and then you could take the derivative yourself. But you're not. We're not going to. Yeah. All right.
In real world, like, do we have some planning on like what our angle is going to be as a function of time? Or?
Yeah, so sometimes we'll have that. In some cases, like our sensors won't be able to read that. So we'll have to take like a finite difference approximation. So you take your theta at a new time minus your theta at an old time. You divide it by the time between those. So it's going to be a little bit noisy, but that'll give you some sort of approximation of it. So usually if you do that, you'll have to apply some sort of smoothing filter, like a moving average filter, or there's like these other like windowing filters that help you do that as well. So you're taking EU120.
Yes.
Right? Yeah.
I love that.
Yes. All right. All right. So we have our first component, right? We have this guy over here. Now, all that we need to do is figure out what this VAB spatial is, right? And this one is going to be a lot less physical. This one is actually going to be just a component of velocity. Let's figure out what component that is. So now what is this lowercase VAB spatial? Okay, so let's just turn back to this formula that we found up there, right? So we found that QA dot was equal to omega AB spatial crossed with QA plus VAB spatial, okay? So we have this term hanging out right over here, right? Now we figured that stuff out right there. Right? That was pretty good. You know, I had this physical interpretation, that was all fine. But we don't exactly know what this VAB spatial represents, right? It's just this mysterious vector. We don't know what it is. So what do we know in this problem, right? Well, we understood that stuff. That was okay. Yeah.
Cross Q and plus.
Oh, that's VAB spatial. So, yeah. So that's that guy there. Yeah, this one. All right.
Wait, that.
Mhm.
Omega is the.
Yeah.
What is it?
So that's going to be the angular component of our velocity. So for spinning around, like how much that spin is contributing to our overall velocity.
There's some up in it.
So there isn't a symbol directly. Usually you'll just write that out as cross reference. Yeah.
This other part comes from the fact that
The whole body is like translating
but
space.
this is that part, right?
The VABS. Yeah.
Oh, that's what you said, because this is also linear velocity, right?
Mhm.
That's why this is just one.
Right. So we're just adding them together to figure out our total velocity. Yeah. Yeah. So this is like the rotational. And this is the translational. Yeah. Great points. Okay. So what do we actually have a physical, like intuitive feel for in this problem? What can we use to actually help us figure out what's going on? Well, we know what this QA dot is, right? We know that that's our actual derivative of the position of our point in space, right? The one that's going to be tangent to our curve. So if it's tangent to our curve, we can figure out what that curve is, and we'll know its direction. Maybe we can figure out its magnitude as well. Okay. So somehow what we want to do is we're going to isolate it. So we have VABS on one side and this very interpretable QA dot on the other side. Okay. So I'm going to try and get this term to drop out. Oops, writing a highlighter here. So try to get this to drop out. So we can get VAB spatial on its own, right? Then we'll have this unknown on one side and this very known physical quantity on the other side. Okay. So how are we going to get omega AB spatial to drop out? Well, maybe something that we could do is we could focus on a very particular point in here that's really going to simplify this problem, right? 0. Oh my God. Yeah, so we're gonna focus on QA equals 0, right? This very special point that will help us drop out this rotational term and give us what we want. Okay. So let's plug it in QA equals 0 and see what's going to happen to the motion of that point in space. So we have QA dot is going to be omega ABS crossed with the 0 vector, which is 0, right? So we're just going to end up with this VABS over there. Okay. So what we find is that when we look at the motion of a point passing through the origin, of the spatial frame, the velocity of that point is going to be what this VAB spatial is. Okay, the velocity of that point is VAB spatial. Okay, so we focused on this very particular point to get it to drop out. And then what we found is that when that dropped out, when we chose that point as the 0 vector, what was remaining was QA dot on one side, our actual physical velocity, and VAB spatial on the other side. Okay, so this tells us that VAB spatial is just going to be the actual velocity of a point that's passing directly through the origin. Okay. So
That's why we did the little trick of like drawing it that imaginary.
Yeah.
Oh my God.
Nice. Yeah.
Q can be any point, right?
Yeah, Q can be any point. Yeah. So this is a relationship that holds for any point in the spatial frame.
Because I thought Q was supposed to be like the R vector, or like you on the axis.
Yeah. So like we like choosing it to be the point on our end effector of the robot because that's what's most informative to us. But if we're actually just trying to figure out like the components of our rigid body velocity, then we can choose it as anything else. Yeah.
Could you make an intuition of why if the rotational component passes through the origin, it's supposed to?
Yeah. So we know that the rotational component of velocity will come from our distance to the origin, right? Like if I'm like spinning this arm over here, this is over here, its distance will determine how quickly that, or how big that rotational component is. So what we're saying is that, all right, now instead of focusing out here, we're just going to bring it right down to this point. So it's not spinning at all. Yeah. Cool. All right. So let's go back to our picture. Let's sketch that out and let's see what we can conclude. Okay. So what I'm going to do is I'm going to focus on this point down here, right? The origin of our frame. I'm going to see what its velocity is right when it's at the origin. Okay. So we're going to say that this point, we're just imagining that it's attached to the end of the arm, right? It's just going to be for like mathematical convenience. So as we spin this thing around, this point is going to be traveling with it, right? We're going to end up with this sort of circular path. So we're just going to keep going around like that. Okay. So we know that its velocity vector right at that origin will be tangent to this circular path, right? So it's going to be pointing right back out over there. All right. So that's going to be its velocity of point at origin. Okay. So what direction is that velocity pointing in? Well, in this case, it's just pointing directly opposite our x vector, right? So it's pointing in direction -1, 0, 0. Okay. Directly opposite from our x vector. Now, how quick is that velocity, right? How fast is that actually moving? Well, we know that our velocity v of a point is going to be equal to its radius from the axis of rotation multiplied by its angular rate, right? By theta dot. Now, what's our distance to our axis of rotation from this point? Well, we just go up here. I'm like, okay, our axis is right there. That's that length L3 that we gave you, right? So the magnitude of that velocity is equal to L3 times theta dot, and it's going in this direction, -1, 0, 0. Okay. So let me just scroll back down here. Yeah. Oh, sorry. Oh, yeah. Sorry. Yeah, of course.
Wait, so it's not that we're just zeroing it out, right? It's that once you rotate with this action,
Yep.
it's just that you evaluate the velocity at the origin.
Right, right. So yeah, it's just because this VABS is it's not an actual physical velocity, it's just something that helps us find a transformation, right? So we know that using this VABS, we can get that relationship cross product plus this little VABS that will hold at any point out there. And just by plugging in a point that gets that rotational term to drop out to 0, we know that that relationship still must be true. So that's where we get that origin from. Sure, yeah. Okay.
Okay. Give an example where you didn't put point before to the semester. How long was it? I'm just trying to see the ball.
Yeah. So we could try that in this case. So if we pick like a point like over here, we would just have to calculate that omega ABS crossed with whatever point that was in the spatial frame. So we would have to take that cross product of our omega vector with that, and then we would subtract that off of. Oh, actually, no, we might not be able to find that in this case. Yeah, because it's going to be pointing in some really random direction, like out there, and yeah, just using like intuition, it would be very hard to figure out what that direction would be. Okay. Yeah, it's like if I'm spinning my arm and I focus on this point, and this is my base frame. Like as I move this over here, this guy could be pointing in any direction out there. Yeah. Okay.
Can you kind of like, can you read over the non V again?
Oh yeah, I'll rewrite that in a nicer way down here. So okay. So what is VABS? Okay. So we figured out that its direction was pointing in the negative x direction, -1, 0, 0, right? And its velocity, how do we figure out the point or the magnitude of the velocity of a point that's rotating in space? Okay. Okay, so let's say that we're trying to figure out the magnitude of the velocity of this point over here. Okay, so it's rotating around theta. Maybe we have another velocity over there. Okay. So
what's actually
oh, that's a V. Like this one?
Oh no, next to the on the left side.
Oh, direction. DIR. Yeah, thanks. That's fine. Okay. So if we have this simple one-dimensional case, how do we figure out the magnitude of the velocity of a point? Well, it's going to be our distance to our center of rotation, right? This distance L. And that's just going to be multiplied by however quick our angle is changing. Right? L times theta dot. Okay. And you can sort of reason about that with units, right? So theta dot is specified in radians per second. So radians are actually like unitless, we say, because they're just a fraction of the way around a circle. So if we're trying to think about that, it's really in the special 1/s. Okay. So if we multiply that by a distance L, which is in meters, right? We're going to end up with units of meters times 1/second, meters per second, right? So it's giving us a velocity back out when we multiply our distance by our angular rate. So what we're really doing in this case is we're saying, okay, the distance to our axis of rotation is going to be L3, and we're spinning the speed theta dot. That's what we do. Okay. So in this case, this tells us the magnitude of VABS is just going to be equal to L3 times theta dot. Does that make sense? Okay. Yeah, so it's in, these are its units. Yeah. Yeah, so radian isn't really, I would say it's like a dimensionless unit. Yeah.
And so like, I don't think I'm quite that much, but, so basically like L3 theta dot is like a scalar, right?
Yeah, yeah.
And then like, we're gonna multiply that by the direction.
Yeah, exactly.
So that's how that's why we get negative.
Right.
L3
L3 theta dot.
Okay.
Yeah. Yeah. So if we want to find our actual vector, VAB spatial, all that we need to do is multiply its magnitude by its direction, right? That's going to finish up this problem. So negative L3 theta dot, 0, 0. Okay. So that's how we find our VAB spatial. We pick that special point, we concentrate on its velocity, we find its direction, we find its magnitude. You just multiply them together. Okay. So altogether, what does this mean for our rigid body spatial velocity? Well, this means that capital VABS, right? Lowercase VABS and this omega ABS. We just stack those two vectors that we found on top of each other, and we're totally done. So we have negative L3 times theta dot, a 0 and a 0, which is what we just found. And then earlier we had found that our angular velocity was 0 theta dot 0. Okay. 0 theta dot 0. All right. And that gives us what our VAB spatial is. Okay. So we've avoided all of that complicated math, right? Now here we had a little bit of explanation, which is why it took a little while longer. But if you just go ahead and you imagine that circle spinning, you can get these pretty much by inspection as you start doing a lot of math. Okay. So does that make sense how we got to this VAB spatial? All right. Sweet. Yeah. That's just me writing it. Yeah. Yeah. Just if you want to, I don't know, convince yourself of this. Yeah. Yeah.
I'm just like trying to understand. So the like corners you found for this like velocity transform, like the points like yeah, holds for every single point. Actually.
Yeah, yeah. Yeah. So these are not our actual velocity, but it helps us find this transformation for any point. For any point, it helps us find QA dot equals VAB spatial hat times QA. So we just plug in the hat map of this into that, right? And all that this thing is doing is it's just taking the components here and it's putting it in that matrix form. And then it gives us a relationship that'll hold for any single point out there. Yeah. Yeah.
So you mentioned over here that you have to think of this capital VABS as a transform, but you might already said that.
Yeah.
But like for individual elements, we just think of those individual elements as parts of those of that cross product you wrote earlier in terms of like the omega ABS will be the rotation component and the small VABS
will be a part of our velocity. Okay. Yeah, will be like a like if I'm moving this whole thing and then I'm moving it over here.
At some point expressed in the apron.
Yes.
Any.
Yeah. All right. Cool. Yeah. Great questions.
Oh, I have no idea. I was looking at this and I kind of zoned out on it. So sorry. But just like I'm not sure if you just talked about this, but so this is not actual velocity. That's just like the big V is not the actual velocity.
Right. Right. It's just it gives us a transformation that enables us to find the actual velocity. Yeah.
And the actual velocity is inside like finding like the G.
Yeah. Yeah. So that's this VABS hat, right? So we said once we had this VABS, if we take the hat map, that was just going to be the hat of this bottom component. So omega ABS hat, and then this lowercase VAB. Right, so that was our VAB, ABC spatial, 0 and a 0. Okay. So all that we need to do now is just plug into the formula for taking this symmetric form of the matrix. And then we just put a velocity vector in there. This will give us something that gives us the velocity of any single point out there on the switching point. This is the transformation for any point to its velocity. Okay, cool. So I think we might run out of time in terms of talking about the adjoint, but we could talk about the. Okay, maybe I don't know. Maybe I can just release a video about it later because I know usually there's people that book the room afterwards. Because last time they were already out here for like 15 minutes. So. Yeah. All right, cool. So let's talk about how we find the body velocity. I think that'll be a good place to finish up. Otherwise, we can talk about the adjoint super quick. We might not be able to have the time to derive it, but we'll see. Okay, so body velocity. All right, so remember, let's just think back to our definition of body velocity, right? So we said our body velocity is something that gives us what the spatial velocity looks like as seen from the basis vectors of frame B, our body frame, right? And this was equal to V of the body hat times our point in the body frame QB. Okay. Yeah. Oh, yeah. Sure. Spatial velocity as seen from body frame. Sure. Yep. And then this VBS is a transformation that gives us this from any point. For any point in the body frame. In body frame. Alrighty. Why don't I just go ahead and copy this diagram out so we don't have to scroll back up. Yeah, sure. Sorry, let me just try and paste here. Paste. All right, 3 times the charm. There we go. Okay. Yeah, just tell me where. Okay, great. Oh. Sorry. This where this is just referring to this QA dot. Sure, yeah. Okay, let me just clean up this diagram here real quick. Get rid of a lot of this stuff that we did last time. Okay. Okay, cool. All right. So remember that last time we were able to find out these nice little tricks for solving for things just by looking at what we were doing when we actually expand out that form of velocity, right? So we expanded out the equivalent of basically the spatial frame, and we found that nice relationship to help us simplify this problem. Okay. So let's try and do the same thing here, right? We know that QA dot in the body frame, I'll just write a bar here for homogeneous coordinates, is equal to V behind body times our homogeneous coordinates in the body frame, right? So if we expand that out, that's equal to our omega A body hat, our VA body is 0 is 0, and our point QB and 1, right, was equal to, I'll just call this VQB at this point, and a 0 underneath. Okay. All right. Yeah, so that's the velocity at that point as seen from the body frame. So okay, maybe I'll just keep it together, right? So that's QA dot in the body frame. Yeah. All right. Okay, so when we multiply this out, we'll end up with a pretty similar expression to last time. Okay, so we'll find that QA dot, as seen for the body frame, is omega AB body hat times QB, which is the same as omega AB body crossed with QB. Just rewrite that. Cross QB is 1 times VAB. VAB body. Okay, so this is a pretty similar expression to last time, so we'll be able to apply a lot of the same tricks, right? So now our only difference is that this thing right over here, when we're looking to figure out our angular velocity from that, that's the same sort of form. Oh yeah, yeah. So the cross came from multiplying QB by omega AB hat, right? So those hat map vectors are ones that are formed with taking the cross product, right? So yeah, so omega AB hat times QB is the same thing as omega AB crossed with QB. Yeah, good point. All right. So what is omega AB B? What does that physically represent? Well, the nice thing here is that we see that this omega AB body crossed with QB, right? That's that same sort of form as this omega cross Q that we were looking at before, right? All that it's doing now is it's working on points in the body frame, right? So all that omega AB is it's the angular velocity vector as seen from the body frame. Okay, and that's just because this form omega cross Q is still there, right? That's still the only way we can apply these angular velocities. And all that it's doing is it's working on points in frame B. So it must just be the angular velocity vector, just as seen from frame B. Okay, so what would that be for this case? Well, let's do the same process that we did as before, right? We know we can break it up into a direction and a magnitude, all right? So right away, we know that the magnitude, omega AB body, we're still spinning at the same rate, no matter which the frame is, right? So that's still just going to be our theta dot, right? Now, what about its direction? Well, this is where these different basis vector directions come in handy, all right? So we see that frame B is actually all pointing in different directions than frame A, right? This was frame A over here. So now, when we're trying to figure out the direction, we want to get the direction with respect to the body frame, right? So direction is with respect to the body frame. And this is just because it's something that's acting on points in the body frame. So we have to think about everything in terms of that frame. Okay, so where is this axis pointing? Where is this axis rotation pointing with respect to these vectors over here? Well, when we look at this axis, right, simply just looks like it's parallel to the z direction. Okay, so that tells us that the direction of omega AB body is just going to be equal to 0, 0, and 1, right? All it is doing is it's just pointing along the z direction in the body. Did you have a question? No. Oh, okay. All right, let's just put those two together. Let's multiply them, right? And that gives us overall omega AB in the body frame is 0, 0, 1 times theta dot is just theta dot. Okay, perfect. So this is our angular velocity vector in the body frame. Okay, so this is referring to that physical quantity. Remember, that axis combined with that rate of rotation. Okay, it's just with respect to these new basis vectors now. Alrighty, cool. So let's go ahead and let's solve for that component of linear velocity. Okay, so let's solve for this VAB body. All right. So let's just go ahead and turn our attention back to this formula up here that we came up with, right? This QA dot in the body frame was equal to omega AB body crossed with that point in the body frame plus VAB body, right? We know that this is a relationship that holds for any point in the body frame. right? This holds for any point in the body frame. Okay, so now, you know, last time we chose the origin, right? Because that was a point in the spatial frame to help drop this thing out to 0. Now we're just going to do that same thing, right? We know how to interpret QA dot in the body frame, right? That's just a physical velocity vector of a point as seen with respect to those basis vectors in the body frame, right? We know that we can send this thing to 0 with a clever choice of QB. And this thing over here is what will remain. Okay? So what we're going to do is we're going to get that term to drop out. We're going to choose our point of interest, QB equals 0. But it's not going to be 0 in the spatial frame, it's going to be 0 in the body frame, right? QB is a point in the body frame. All right, so that is the origin of the body frame. All right, cool. So physically, when you perform this multiplication, right, QB dot in the body will be omega AB in the body crossed with the 0 vector. It's going to be 0. I'll leave us with VAB body. Okay. So what this tells us is that VAB body is the velocity oh, yeah, that should be it. Which one? Oh, yeah. Thanks. Yeah, so VABB is the velocity of the body frame transformed to the body frame. Transformed to the body frame. Okay, so let me clarify. This is the spatial velocity. Okay, so we're saying what we're going to do is we're going to pick this point right over here, right? We're going to pick that to be our QA, right? And we're moving that around in space. So what this is it's going to be the spatial velocity of our body frame. We start moving that towards QA, right? And all that we're doing is we're transforming that into our body frame. Okay? So what that gives us is the spatial velocity of the body frame with respect to the basis vectors of the body frame. Okay, so that's what this VAB is. All right. So why don't we go ahead and just do the same thing that we were doing before, right? Check the magnitude, check the direction, multiply them. Then we'll be all good to go. Okay. So before we do that, do you guys have any questions about how we got to this point? Right. So we're looking at like where this point is going in space, right? Like this vector, where that's pointing, right? Because that's going to be the spatial velocity of our body frame. And then we're just representing it with respect to these basis vectors over here, instead of representing it with respect to the text. Yeah.
So you're finding this transport. You like omega AB as omega AB was
Yes. Right. So that term will just tell us that, all right, that's got to be the angular velocity. Yeah, sure.
It was something I was also thinking about, but this one I wasn't thinking about, but also didn't know that I didn't know. But implicitly all questions are
Good answer. Very diplomatic. All right, I'll give you guys just a sec to copy this down. Okay. So let's go ahead and find what that vector is real quick. All right. So what we're going to do, we're just going to go back up here, right? And let me just write this in a good color here. So we're spinning around this path, right? Body frame is tracing this circle out as we spin this arm, and we focus at this point on the origin. Right when it's at that point, we go, okay, where's that vector pointing? Well, right over here, it's pointing opposite the x direction. Okay. So our direction is in the negative x direction. All right. Now our magnitude, we're just going to work in the same way as before. It's going to be our distance to the axis of rotation multiplied by our rate of rotation. Okay. So the magnitude of VAB in the body frame is going to be our distance to our axis of rotation, which in this case was that length, L2. And we're going to multiply it by the rate at which we're turning around that. which is going to be L2 times theta dot, right? So what we have is L2 times theta dot in the negative x direction. Okay. All right, so I'm just going to rewrite this down here. So our direction is going to be the negative x direction, right? Negative 1, 0, 0. And our magnitude of the AB body is going to be the distance to our axis of rotation, which this time is L2, since we're focusing on the body frame, not the spatial frame. We're going to multiply that by that same angular rate, theta dot. Okay. So together, let's just multiply these guys, and we'll get out what our total vector is. The AB body is going to be equal to negative L2 times theta dot, 0 and 0. Okay. So now we have everything we need to put this vector together entirely. Do we have any questions about our process for finding this one? Yes.
So we found the ABB, like the velocity from the perspective of scale, right?
Yes.
Do we still have to locate it to make it?
Yeah. So what we did is when we were looking at it right over here, it actually turns out that like in this configuration that they've drawn it in, this vector and this vector are aligned. So we're actually representing with respect to this x over here. It just so happens to be that those two are pointing in the same direction. So when we're describing that direction, we always do it with respect to this B frame. Yeah, great point. Yeah.
If they weren't aligned, you just take like components.
Yeah. So you would just look at where this vector is going with respect to the z of the B frame, y, and x. So, yeah. All right, superb. Okay, so we have our VAB, we have our omega ABB. Okay, so it tells us VAB in the body frame, which is equal to those two stacked on top of each other. VAB in the body, omega AB in the body, which is then equal to negative L2 theta dot, 0, 0. And what was our omega? 0, 0 theta dot. 0, 0 theta dot. Okay. So that gives us this vector in the body frame. Okay, that's our body velocity. All right. So let me just write a summary of what we've done here and how this relates to just everything we've been talking about so far. All right. And then hopefully this concept will come together. Okay. So summary. Here's what we found. Well, we know that if we pick a point in the spatial frame, pick point QA in the spatial frame, we're going to be able to find its velocity, QA. So its velocity is QA dot equal to the hat map of VAB in the spatial frame times QA in the spatial frame. Okay. And that was that vector, this hat map is the hat map of that vector that we found earlier. VAB spatial is going to be the hat map of this lowercase VAB spatial, omega AB spatial, right? Hat map of the thing. Okay. Now what about the body? Well, if we pick a point QB in the body frame, we can find its spatial velocity as seen from the body frame. Its spatial dot from the body frame is its corresponding point in the spatial frame, take its derivative, transform it to the body frame, equal to VAB body at times that point in the body. Okay. So what we did is we found these vectors, VABS and VAB body, right? We found their components. Now all we would need to do is just take the hat map and we can apply it to any point that's out there. You could find the velocity at any point on the spatial body. And yeah, I think that should be about what we have time for. So yeah, if you guys have any more questions, yeah, just let me know. I don't see anyone outside, which is good. So yeah.
What is the adjoint?
Yes, what is the adjoint? All right. So oh yeah, of course. Yeah.
Also, can you smile?
No.
Perfect.
Best TA award.
Oh, thank you. All right. Oh, do we have any questions about this stuff before we talk about the adjoint?
I just have a question.
Oh, yeah, of course.
Is this not intuitive for me? The problem is like, if you pick 8.0, right?
Yeah.
This is saying that once you're at the 0 point, the linear velocity that the angular motion is contributing is nothing. Is 0. What the heck?
Yeah. So it's it's kind of weird. Right.
You're rotating a point that is on the axis. Like that's not moving at all.
So that's where our omega term will. So okay, yeah, let me go back up here. So so we're not saying that it's not moving. We're saying that its velocity at that point will be given by this VAB spatial. Okay. So it's not going to have any components from that omega AB cross Q, right? Because in actuality, when we do that omega cross like with R, right? That R is our distance to the axis of rotation. Okay. So in this case, we still actually have a distance when we're at the origin, right? So it's not going to be perfectly the same thing as that omega cross R case, right? So we still have that distance going on. So if we were to use omega cross R to figure out what it would be, then it would be a little bit different. So it would be the distance from here up until that point over there is what we need, right? But when we're doing this omega AB cross Q, we're saying that this angular velocity vector is not going to do anything for us. We're going to need this additional term, this little VAB spatial, to take care of that velocity. So it's not that it's going to be completely still. It's going to have a velocity, and it's going to be like this correctional term, VAB spatial. Yeah, so it's just essentially something that's like shifting our whole system. So like normally what we have is,
That was already present in the motion. Right?
Yeah. So normally like if we have something that's moving around like this, right? We need that vector R, which is our distance to the axis of rotation, right? But we're not always going to have our axis right over there. And this thing isn't always going to be still. So what that extra VAB spatial does is it accounts for that overall motion and for that distance to the axis. Yeah. Does that make sense?
Okay, so I'm just getting to the conclusion that this only works because we have a body frame.
Yes. Yeah. So it's only working because we're representing all these points of the body frame. Yeah. Sure. Yeah. Okay. So I don't think anyone is next. So we could talk about the adjoint for like a couple minutes real quick. I'll just give you guys like an overview of what it is, and then yeah. What's up? Wait, sorry. I know you just came in. Are you here for something afterwards? Or?
No, I'm just here.
Oh, sweet. Okay, cool. Like I didn't want to be saying that, and then you're like, I was in this room. Okay. So let's talk about the adjoint real quick. All right. So far we have a VAB spatial, a VAB block, right? And this is a vector in R6, and this is going to be a vector in R6. Okay. So what we want to figure out is if there's some really convenient way, like some single matrix that will help us transform between these two, right? So is there a matrix that helps us transform? So let's transform, right? Because the problem is it's not going to be those G matrices, right? These are vectors in R6. Our G matrices are 4x4 matrices, okay? So we can't just apply G. Can't just apply G. So if we want to go from a 6x1 vector to another 6x1 vector, we're going to need some sort of 6x6 matrix, right? So we'll need a 6x6 matrix. All right. So let's talk about what that matrix is. Okay. So we have a special matrix called the adjoint that helps us do this. Okay. So adjoint of G will help us perform this transformation. Okay. So it transforms rigid body velocities. Okay. So what's going to happen is if we have a VAB spatial like this, let me just make sure I get this direction right. Yeah. Okay. So if we have a VAB spatial and a VAB body, and we want to switch between these two very freely, we multiply the body by something called the adjoint transformation. Okay, so VAB body. And this is something that's acting directly on these 6x1 vectors. All right. So adjoint acts on the vectors. All right. It's not interacting with those hot map matrices at all. It's just a pure single matrix multiplication that's going to be doing this transformation of velocity from the body frame into our spatial frame. Okay.
And then GAB.
Yes, that's our GAB. Okay. And the reason that we write adjoint of GAB is that this transformation will only depend on components of GAB. We don't need any information about the velocity. It's going to be purely in terms of the rotation matrix, right? So we have GAB is like RAB 0, PAB 1, right? It's only going to depend on these components in here. We don't need anything else. Okay. So the adjoint of GAB, yeah, I don't think we have time to write this here, but yeah, maybe I'll make like a little video and then send it out. That's equal to RAB 0, RAB, PAB hat map, right? Turns it into a matrix times RAB, right? So using this special matrix right here, we can go between these different velocities just with a single matrix multiplication. Okay. So it makes it very easy. Makes it very easy to transform between velocities. All right, cool. So, you know, actually, don't have time to do that. All right. You know, maybe we'll just talk about like one note real quick about another form of this transform that's very helpful in the homework. All right. So all the way at the beginning, we define this VAB spatial to be equal to what should we call it? It's GAB dot, GAB inverse, right? And we have, oh yes, thank you. And we have VAB body is equal to jumping the opposite direction, GAB inverse, GAB dot. Okay. So if we want to figure out a transformation between these associated vectors, right? These are still in hat map form. We want to figure out a relationship between the vectors. Maybe we could just start by looking at a relation between the hat maps. So look for a way to relate these. Right? What can we do about that? Well, here's what I'm going to do. It's going to be a little funny. VAB spatial hat. Okay, so we know that it's equal to GAB dot, GAB inverse, but to the adjoint relate to linear algebra adjoint. So this is a different adjoint to in linear algebra. So if you guys have done, I don't know, you might have done this in 16B. I never took 16B, but you might have talked about like the complex conjugate adjoint. So there's something called like the conjugate transpose.
Yes.
Oh yeah. So conjugate transpose adjoint. So it's not that, yeah. So that's essentially you take the complex conjugate of every entry in your matrix and you take the transpose. That's a different type of adjoint. So there's a lot of different adjoints in linear algebra. All of them have different purposes. This one in particular, you know, will help us transform between these. And the only reason that we use the word adjoint just means that it's useful and related to our original matrix. Related to our original, right? Like if two ideas are adjoint to each other, that means that they're closely related. Like one comes from the other, you could say. Okay, so that's the only way that this word adjoint really pops up here. So a lot of the times they'll refer to different things. If you say adjoint in this class, it's going to be, you know, this R, P hat R, 0R that we're talking about. What's up? Oh, original. Original. Yeah. But yeah, if you see adjoint in another math class, then maybe it'll be talking about conjugate transpose. I don't know why they're all the same. It's kind of weird. Yeah, good point. Okay, so how can we modify this VABS formula slightly to relate it to this other VAB model? Well, VABS, something kind of neat that we can do, right? As we know, GAB is invertible. So why don't we multiply GAB and GAB inverse, right? That's just the identity, right? It's not actually changing anything in our formula over here. Okay. And now, so we're multiplying this whole thing by GAB inverse. What I'm going to do is I'm going to move these parentheses over. I'm going to say instead of doing that first, we're going to do that first, right? So we're going to do GAB inverse, GAB dot in parentheses. Because matrix multiplication is associated. We can put these parentheses anywhere we want. It's going to work out fine, right? So what is this actually giving us? Well, if we look at this on the inside, GAB inverse, GAB dot, what's that equal to? That's equal to our VAB body hat, okay? So GAB, VAB body hat, GAB inverse, okay? So we actually have this transformation between these two matrices, right? Between VAB spatial hat and VAB body hat, using this, other transformation, like GAB over here, okay? So the reason that we really like the adjoint is that it allows us to do this entire thing just with a single matrix multiplication, right? And it also keeps it in vector form, right? So this tells us that like VAB spatial, like not hat, is equal to VAB body times GAB inverse, the V map of that, right? And that's going to be the same thing as taking the adjoint of GAB and multiplying it by VAB body, okay? So this is like a formula right over here, this identity, the adjoint being the same, taking the V map of this transformation. That's something that comes up a lot in the homework assignment that you guys might have seen, I think, especially in question 4. Yeah.
The arc still will be everybody inside.
So which one?
Inside.
Oh, that, yes. Yeah. So what this also means is that like if you ever see something pop up that's like adjoint GAB times VAB body, you try to take the hat map of the entire thing. That's just equal to the hat map of this guy over here, right? So that's just equal to GAB, VAB hat, GAB inverse. Okay. Yeah. So that's something I think that comes up in problem 4. Like you sort of apply the hat map to different components, like in the sun, and then this is one thing that you do to help reduce. So the actual formula for the adjoint in terms of this R, P hat R, 0, and R is something that comes directly from this formula. You essentially just multiply all these guys out, and then you take the V map of that all the way at the end, and that's going to give you what you need. Yeah, I think we'll probably leave it there. But yeah, do let me know if you have any questions. So, yeah. Oh, sorry, that just means that we're taking the hat of this entire thing inside. So it's like if I wrote like a big hat over that entire thing. All right, start recording.